A Wall for the Future, Mech design project of Team 5, consisting of Jackson Jandrew, Ken Liu, Gu Tai, Addison Collins, Austin Bennett, and Austin Rowland.
Our group was tasked with developing a wall structure that could withstand several different types of elemental forces. In order to accomplish this, we separated our group up into 3 smaller groups that would each investigate different aspects of the wall design. We brainstormed several ideas, and many were investigated further, and these were brought towards the group meeting where we selected 3 designs to fully investigate. The design our team settled on was what we called the Scissor Lift. Its rapid deployment system and high mobility enabled it to be the most versatile wall possible.
Further details of this wall will be elaborated upon, including the preliminary characteristics of the design in further slides. The first step of our project is to identify the product goals and requirements as set by the customer regulations. It is crucial to clearly define these guidelines early so that the rest of the project can be set around them. The final product we deliver can vary in many ways, but ultimately must meet these goals. The customer had these requirements. The wall was to be built as a rapid deployment system. The customer has not specified any further on rapid, so we will assume it to be relative and try to keep the deployment time in our minds as we move forward. Each section of the wall is to be 6 feet wide, 25 feet tall, and 40 feet long. Every 1,000 feet along the wall, we must have an elevated platform for supporting 2 workers, sensors, lighting, and equipment, etc. This platform must be 10 feet above the wall and be 5 foot by 5 foot on top. Our wall segments must be able to be placed in such a manner that allows for T's, crosses, and corners to be made at their unions. Also included in the wall must be the capability for adding a door panel every 2,500 feet, which measures 20 feet wide by 15 feet tall. The system must allow for at least 5,000 feet of wall, but hopefully we will be able to design ours to handle much more than that. It must be designed to be usable anywhere in the contiguous United States. This will vary our weather and climate factors as well as laws and regulations. The wall must also, in some form, be fireproof. Fireproofing includes being resistant to heat, as the wall must remain stable and the catwalk must be usable during a fire. In addition to the fire, the wall must be able to handle up to 5 feet of water on one side of it. We are asked to design the wall to resist maximum wind and ice loads as can be measured in the contiguous United States. The unit should be mobile and constructed with minimal man hours, but again, the customer has not defined minimal, so we would consider this a request for time efficiency. The wall must allow for manned access across the top of it and allow access to elevated platforms along it. Transportation of the unit must comply with Oklahoma road laws and regulations, as well as the catwalk behaving in accordance with OSHA rules and regulations regarding elevated platforms, catwalks, ladders, and stairs. The legal restrictions regarding the project are crucial, as we will not be allowed to operate unless these regulations are met. The most rigorous are the OSHA safety and hazard rules governing catwalks, ladders, elevated platforms, and stairs. The restrictions are as follows. Any working surface 4 feet or higher must be protected with guardrails at least 42 inches tall. 3.5-inch tall toe boards must be installed on all sides of the platform. Guardrails must be able to sustain up to 200 pounds of force applied downwards or outwards. The platform height cannot exceed 4 times its base width. The platform must be tested to 4 times its rated capacity. Stairs must be at least 16 inches wide, 7 inches deep, and have no more than 10 inches of rise between them. Stairs can support 5 times the normal anticipated live load. Self-closing gates are required around openings unless nobody can fall directly through the hole. Ladder rungs are spaced not less than 10 inches and not more than 14 inches apart. Non-self-supporting ladders must have both side rails supported. Ladders that extend over the platform must extend more than 3 feet above the platform. Ladders must also support up to 4 times their intended load, and ladders higher than 20 feet in height shall be provided with a cage. Another set of regulations to comply with is DOT rules regarding the transportation of the wall system. Axle weights are as follows. Tandem axle weight is limited at 34,000 pounds, and a single axle is limited at 20,000 pounds. The standard road widths that the roads must comply with is 8.5 feet wide per lane, and the minimum bridge height is 4.5 feet underpass. The next step in our process is to consider and estimate the types and magnitudes of loads our wall will be experiencing. The types of loads we are asked by the customer to consider are water, wind, snow, ice, and live loads. The maximum of each of the load types is followed. 312.13 psf for the water load, 139.11 psf for the wind load, and 125 psf for the snow load. The ice will be left out of calculations for now because it is determined by how much surface area the structure will have, and we haven't determined that yet. We have addressed the fact that our system will be experiencing shear, bending, and torsion forces, both from the load and from other components pressing against each other. These values will be further calculated in phase 2 of the design, as many of them depend on the geometry and materials of the system. We must also make assumptions about the deployment of our system in order to design and further calculate based upon it. The main assumptions we will be making are that the forces generated on the system will be maximum and acting all together at the same time. Also, that the system will be deployed on solid and flat ground. This is for the purposes of calculations. In reality, the system will be able to be deployed on nearly any terrain. And we will also assume the design to be fixed in place and not slide. However, tipping forces will still be considered.
When looking at our multi-element interfaces, There are two areas we have to consider. The first interface to be considered is interfaces between different materials. In our designs, some examples of these interfaces are contact between concrete and metal, and fastening mesh to metal pieces. The second interface we have to consider is more complex part interfaces. Our designs will likely have many of these, but a few examples are our 4-bar mechanism and bolts and bolt holes. The 4-bar mechanism will be used as a latch for our door. With bolts, we have to consider the size of the holes and the stress that we put on each of the bolts. In each design, besides the customer requirements, we decided upon a couple of common elements we wanted. First, to aid both the fire resistance and the reduction of the risk of tipping, we wanted the upper sections of our wall panels to be made of a porous, fire-resistant mesh. This would reduce the force from wind while still maintaining fire resistance. The second common element would be the use of a 4-bar element to latch the door. In order to decide upon the best approach, we used a design matrix to analyze each element of the various designs. This decision matrix will be discussed in an overview of each wall design.
One of the three designs that we had is the scaffolding design. This design utilizes scaffolding to build the wall. After it is built, it will also double as support for the wall. The scaffolding will comprise of couplers 3 feet in depth apart, 6 feet in width apart, and 5 feet in height apart. These couplers will be connected by solid metal bars and a metal platform that can be placed wherever necessary in addition to the catwalk that is 20 feet above the ground. The railing for the catwalk is formed by the metal bars that extend upwards to the specified height of the wall at 25 feet. To include the towers for the wall, more metal bars will simply be added atop of the normal scaffolding to create a tower structure. The wall is also to be metal and can be sectioned into small pieces to allow for easier assembly and will lay on one side of the scaffolding and will be held by connecting pieces. Extra measures such as a tarp to keep floodwaters away from the ground of the wall will also be included. Similar to other designs, the 4-bar mechanism will be used as a latch that will close the door of the wall. For machinery required, this design does not require much. The only necessary machinery required when this wall is being put up is something to move the metal pieces upwards to make it easier to assemble. The scaffolding can be put together by human labor, and this will also create the base that is needed to keep building the wall higher. No heavy machinery such as cranes or bulldozers are needed for this design. The good things about this design are the manufacturability and portability of it. There are very few unique parts to this design, and practically every single piece has already been manufactured and can probably be mass-produced already. This could mean that the cost of this wall will be significantly less than a design that will require unique pieces that need to be integrated into a production line. It is also very portable as each individual piece is also not too big. This allows the pieces of the wall to be easily placed in trucks for transportation. There are also some downsides such as the slow assembly speed and high manpower requirement. Due to the sheer number of pieces this wall contains, the assembly of the wall will be much slower than other designs. Also, each piece will need to be assembled by hand, which slows down the process even further. Having more people will lower the assembly time, however, it will also increase the cost due to having more labor.
Another design we had is the scissor lift. This design was made with the goal of being quickly deployable. This is reflected in the fact that each section is already fully built and deployment only lasts a few minutes. The scissor lift consists of several arms that cross like X's, called scissor sections. Each pair of arms are connected at the intersections in such a way that they are allowed to rotate about the intersection. The lift uses hydraulics to move the scissor sections upwards and pull the metal wall sections into place, similar to a garage door. The connections on the sides of the X's will be locked into place with struts once the wall is in place. This will keep the structural integrity of the structure when pressure is released from the hydraulics, as it's unsafe to rely on such a system to hold for an extended amount of time. The catwalk is held by the top scissor sections. Each section of the lift will have 4 scissor lifts that parallel the short end of the wall section. There are 2 lifts on one side of the center point and 2 lifts on the other side. To minimize differences between sections, the space between the lifts will allow space for a door. The height of each scissor section will be approximately 6 feet. After 2 full scissor sections and 2 halves, the lifts will be 24 feet tall each, including the bottom of the section. The wall will total over 25 feet. The 4-bar element design required will be utilized as a door hatch to close the door. The hydraulic pistons will be placed on the scissor sections as per typical for scissor lifts. The major pros of this design is its low deployment time, low manpower requirements, and high portability compared to other designs. The cons are its complex manufacturability and its price due to hydraulics.
Our third and final design is the hybrid design, which bridged the gap between the extremely sturdy designs and the ideas which could be built extremely fast. This design used several concrete blocks spaced out every 15 feet, which had slots on the top which allowed for a pole to be placed and extended upwards. The poles would support the catwalk 20 feet above and would provide contact points on which to mount the fireproof fabric. The concrete blocks would extend about 6 feet high and would also have slots on the side which would allow for two 15-foot by 3-inch by 3-foot metal plates to slide in, preventing water from penetrating the wall. These plates would have a groove which allowed them to settle into each other, maintaining a waterproof seal. The poles would set 5 feet into the concrete and extend 19 feet above it, supporting the catwalk. The catwalk would also attach diagonally to the concrete, allowing for support on both sides. In this design, we would use the 4-bar element as a latch that would close our door, and there would be several of them going up the hinged panel. In order to set up this design, we would need a large bulldozer and excavator in order to lift the concrete blocks off the truck and put them in place on the ground. After that, the machinery would be minimal for putting the bars and fabric in place, but we'd make use of the excavator again when putting the catwalk in place. The best part of this design was how well it struck a balance between everything. This is meant to be a one-wall-fits-all kind of project, so the hybrid not having any major weak points was a big advantage. The hybrid could be put up quickly and would be relatively easy to account for varying load conditions. It also required very minimal equipment to install and would be extremely easy to manufacture. Some of the downsides to this design were how big the concrete blocks needed to be in addition to the length of the metal panels.
After identifying our 3 best designs, we came up with a design matrix to objectively rank our 3 designs. With our design matrix, we came up with 10 categories to look at. Each category has different weights to it, from the most important rating at 1 to the least important rating at 0. The weight of each category is determined by the consensus of the team members. One of our design categories is how well we meet the requirement of our customer, which we rated at 1.0. This is due to the fact that even if our design is a masterpiece, if it fails the criteria listed out by the customer, it is a failed design. The most important part of our design is how fast we can assemble it. This is pretty much what this project is about. Our designs are supposed to be portable and be able to be set up fast. We have created 2 categories, one for the portability design and the other for the speed of the assembly. Due to the importance of this category, we gave them 0.8 and 0.7 weight respectively. Next, we viewed that manpower, speed of assembly, and number of parts go hand in hand with each other. If it takes a significant amount of workers and the design consists of a lot of parts, then it is most likely a poor design. So we gave manpower and speed of assembly a weight of 0.7 and number of parts 0.4. Next, we have ease of design, maintenance, and cost. Ease of design refers to the details of our design. This can include how we set it up, what can go wrong with the design, and what is the technical specifications are for this design. We found that this category is very important due to the fact that if the design is deemed extremely difficult, then it will be extremely difficult for us to detail out the designs in the time span we are given. So we decided to give this a weight of 0.6. We found that the manufacturability and the cost of the designs to be not as important due to the fact that it was not outlined well for the project. Next, we ranked maintenance to not be that important due to the design being a portable wall. And as the wall would be torn down and set up when and wherever, we gave it a weight of 0.2. Finally, we found that the equipments can be used, but large machines are not preferred, so we gave this a weight of 0.5. For scaffolding, we found out a wall made out of scaffolding would be extremely portable and can be made to be very sturdy. We gave scaffolding a 9 out of 10 for portability, 8 out of 10 for cost, and 10 out of 10 for manufacturability due to the fact that scaffolding would consist of just rods and couplers. This means that it is extremely portable and requires little to no machinery, so we gave it a 7 out of 10 for equipment required. But a scaffolding wall fails in a lot of other categories. For example, scaffolding requires an insane amount of manpower since everything has to be assembled by the hand. Furthermore, it would have an extremely slow assembling speed due to that fact. We gave it a 2 out of 10 for manpower required and a 1 out of 10 for speed of assembly. Overall, scaffolding got a score of 30.8 out of 55. For the scissor lift wall, this design we found out extremely interesting due to the fact that it's relatively portable, strong, and has a fast assembly time and requires little to no manpower and machinery. Imagine a scissors lift before it is erected into a wall. It would be flattened down. So we picked that we can most likely carry 2 to 3 sections of the wall per vehicle. For the portability of the design, we gave it a 6 out of 10 due to the fact that it is relatively portable. We were thinking of using hydraulic systems to expand the wall upwards that this would require little to no manpower and most likely no machinery. So we gave it a 9 out of 10 for manpower required and a 7 out of 10 for equipment required. Due to the fact that the scissor lift would be erected by hydraulic system, we would only be placing a wall and the wall would rise on its own. We gave it a 9 out of 10 for speed of assembly. We rated the scissor lift an 8 out of 10 for number of parts due to the fact that it would just be the scissor lift itself, the plates, and a protective cover for the fire. We also gave it a 6 out of 10 for cost and a 4 out of 10 for manufacturability due to the fact that there would not be pre-existing scissor lifts out there that would be extremely sturdy. Overall, the scissor lift wall got a score of 40.9 out of 55. Our final design of the hybrid wall we found to cost less than that of the scissor lift, and it is more portable and manufacturable than other walls. This design meets the criteria of the customer by being the strongest auto design and relatively portable for what it is. So we gave it a 10 out of 10 for meeting the requirements. Due to this design consisting of a cement base with metal planes as the wall, the cost of the design would go down because of the components. We gave it a 7 out of 10 for the cost. The portability of the hybrid would pretty much be the concrete base, which are smaller than the scissor lift, and the metal plating, of which both are smaller and compact enough to fit in semi-trucks. So we gave it a 7 out of 10 for portability. We believe that these parts could be easily manufacturable because metal plates already exist and the cement base which just involves creating the mold for it. So we gave manufacturability an 8 out of 10. The parts of the design consist of the metal plates and the concrete block base, so it is a 6 out of 10 for parts. For the manpower and speed of assembly, it goes down due to the fact that these parts weighs a lot, so the trouble will be placing them in the correct spots. So we give it a 5 out of 10 for both. The design of the hybrid will most likely require some sort of machinery like a bulldozer or a small lift, so we gave it a 7 out of 10 for equipment required. Overall, this design received a 39.9 out of 55. Both the hybrid and the scissor wall came really close to each other, but the factor that decided the best wall for the project is the speed of assembly, manpower, and portability of the design. All of which the scissor lift wall fits all of those with flying colors.
After much consideration, we settled upon the scissor lift as our final design. Although the scissor lift design is the best option, it does have its issues to be addressed. Its lightweight design gives it potential for tipping, which needs to be accounted for. The attachment and use of hydraulics also needs to be outlined more clearly. While we have a general idea of how the wall sections will connect in T and cross sections, we have yet to consider certain aspects, such as how to maintain a watertight seal at the base. Not only did this design score the best in our decision matrix, but we felt it also struck a good balance of strength, speed of setup, and portability.